We have talked about Newton's first law, and we have talked about forces and force diagrams. So now we are going to bring those two ideas together. At the end of this, you should be able to use Newton's first law to determine the magnitude of unknown forces, identify situations where Newton's first law applies, and draw accurate force diagrams that show balanced force situations. So in your notes, make sure you have these summary questions answered. Recall that Newton's first law says that an object in motion will stay in that same motion, and an object at rest will stay at rest. This is true until some outside force of our system comes along and acts on that object. What we are really saying is that as long as there is zero net force acting on an object, its motion will not change. So what do we mean by net force? An object can have more than one force acting on it at any given time. Take these guys for instance. We've got three pretty hefty guys pulling on this rope. But look at that knot. It's not moving. And over here on the other end, she's just playing. Whatever, fellas. We can take those forces and essentially add them together. This combination of all of the forces acting on an object is called the net force. Newton's first law is all about objects that are not changing their motion. This can only occur when the net force is zero. Take a book sitting on the table. It's not moving. What are the forces acting on it? Gravity is pulling it down, and the table is pushing it up with a normal force. Think about a tug of war. How do you win? One side must be pulling with more force than the other. How do you have a tie? Both sides must pull with the same amount of force, just in the opposite direction. This is basically what is happening with gravity and normal forces here. The two forces essentially cancel each other out. This is what we mean when we say the net force is equal to zero. And when the forces balance, Newton's first law says an object's motion will not change. So take this mass. It's at rest in my hand. What does that mean about the forces? Are there any forces acting on it? Well, this is the back of my classroom, so we know we're on Earth. That must mean that gravity is acting on the mass. And it's sitting on my hand, which is a surface, so there must be a normal force pushing it up. Since the mass is not moving, according to Newton's first law, the net force acting on the mass must be zero. And net force means that the forces must be balanced. If the forces are balanced, the normal force pushing up must have the same magnitude as the gravity pulling down. So how could we show this in a force diagram? Remember that arrows coming out of the box on a force diagram are vectors. Vectors represent the direction and magnitude of the forces they are describing. To show that the normal force and the gravity are the same magnitude, we will draw the vectors the same length. A lot of times on quizzes or tests, there will be a question that says, draw a labeled force diagram showing all the forces acting on an object. In a question like this, here's what I'm looking for. First, you must correctly identify all of the forces. Then you will need to draw the labeled vectors that begin at the box and point in the direction each force is acting. These forces must be drawn with a ruler and must be the correct length for the scale of your picture. Let's take Tom and his box. He is pushing a box with a force that happens to be 1/2 of the box's force of gravity. The box does not move. How do we know that the forces on the box are balanced? Well, remember that according to Newton's first law, an object at rest has no net force acting on it. No net force means that the forces are in balance. So anytime an object is at rest, the forces must be balanced. This is an important point to remember. If an object is not moving, the forces are balanced. So what would a force diagram look like? Well, a force diagram for what? The problem gives us what we need to use as our system, the box. So we are going to draw a force diagram for the box. Pause for a second and list the forces you think are acting on the box. We are going to assume that Tom lives on Earth, so there is gravity pulling down on the box. The box is sitting on a level surface, so there is a normal force pushing up on the box. Tom is pushing on the box, so he is applying a force to the right. So why isn't the box moving? There must be some force keeping the box from scooting across the floor. There are two surfaces moving against each other, so there must be a friction force acting to the left. The first step in drawing a force diagram is going to be to shrink our system down to a little box. In this case, the system is a box. So let's make that box just a little bit smaller. Gravity is our first force, and we know that it always acts down. Our vector starts on the box, and we are going to use a ruler to draw the arrow straight down. Make a note of how long you draw your arrow. On paper, 2 centimeters is a good place to start. The normal force we decided would be acting straight up. Now, how long do you think we should draw our arrow? The box is at rest, so it is not moving up or down. So the vector that we draw for the normal force will be the same length as the vector we draw for the gravity force. Our gravity vector was drawn 2 centimeters long. We will draw our normal force vector 2 centimeters long. Use a ruler. Notice how the forces acting in the vertical direction, or up and down, are equal in magnitude, but opposite in direction. Imagine a tug of war with these two vectors. No one would win. The same thing happens with forces. Neither force is strong enough to overcome the other, so the box does not move in that vertical direction. Now let's look at the applied force. Tom is pushing on the box with a force to the right. But how long should we draw our vector? Notice in the problem that it says the force Tom applies is 1/2 of that of the force of gravity acting on the box. Since we drew our gravity force vector 2 centimeters long, we will draw our applied force vector half of that, or 1 centimeter long. Okay, one more. What about our friction force? What do we know about that? We know that the box is at rest. That means that the forces are balanced. So the box is not moving in the horizontal direction either. That must mean that the friction force has the same magnitude as the applied force, since it is moving in the opposite direction. The vector we drew for the applied force to the right was 1 centimeter long, so the vector we draw for the friction force to the left must also be 1 centimeter long. Shall we practice a few? Pause the video and draw a force diagram for each of the situations described. Okay, so what about the first problem here? We have a projector hanging from the ceiling. First question is, what is our system? The question mentions a projector and a ceiling, so we could pick either one. The projector is going to be a lot simpler to describe, so let's go with that. All right, so what forces are acting on it? Our classroom is on Earth, so gravity is going to be pulling it down. What is holding it up? The projector is not on a surface, so there isn't a normal force. In this case, we would have a tension force pulling the projector up to keep it from falling. So we have a tension pulling up and a gravity pulling down. Any other forces? I can't think of any. Are the forces balanced? Well, the projector is not moving, so yes, they are. So when we draw our tension and gravity vectors, we're going to draw them the same length. Now keep in mind, it does not matter how long we draw them. As long as both are the same length, we are good. And don't forget your ruler. Now what about Tom and his box? This time, instead of the box not moving, it is moving with a constant motion. Do you think this is covered by Newton's first law? An object in motion will stay moving in its same motion, right? That would mean that the motion is constant. So anything moving with a constant motion will follow along with Newton's first law. This means that the forces acting on it will be balanced. So which forces are they? We still have gravity and normal. Tom is applying the force, and we still have the same two surfaces moving against each other. This gives us gravity, normal, applied, and friction. And again, they are balanced in both directions. So again, we want to draw the normal and gravity vectors the same length, and the friction and applied vectors the same length, but half of the normal and gravity. What is really interesting here is that the force diagram for this situation is the same one that we used for the box when it was not moving at all. So what about Bob in this third situation? He comes along and starts pushing in the opposite direction as Tom. The box stops moving. An object at rest has balanced forces acting on it. That must mean that Bob is exerting the same force that Tom is. Gravity and normal aren't going to change, but what is? Instead of friction force pushing to the left, the box is going to have two applied forces acting on it. Tom is pushing to the right, and Bob is pushing to the left. Okay. So this force diagram will look just like the second one, but with different forces acting on it. I bet these objectives didn't look quite so involved at the beginning of this, did they? There really is quite a bit that is hidden there in Newton's first law. So, can you use Newton's first law to determine the magnitude of unknown forces? Can you identify situations where Newton's first law, Can you identify situations where Newton's first law applies? And can you draw accurate force diagrams that show balanced force situations?